Okay, so today we are gonna focus on Black-Scholes formula, and more specifically we are going to focus on its derivation. Okay, I'm not going to go through how it works, what it is good for or so. I expect that you already know how to use Black-Scholes, but today I'm gonna go through how to actually derive Black-Scholes, because that is the most threatening point about Black-Scholes. In general, we can say that there are variety of approaches that you can apply in order to derive Black-Scholes, but in this video I'll just show you one which is called martingale approach. It has something to do with measure and measure change. So I expect that you have some understanding of the most important concepts of stochastic calculus, such as Girsanov theorem and Ito's lemma. Okay, because those will be the cornerstones of the derivation. Okay, well, I'll start with the definition of the payoff. Okay, let's assume that we have some call option that at maturity pays maximum of the value of the stock at option maturity and strike, minus strike and 0. Okay, so the maximum of those two numbers, maximum of this value and 0. Okay, so the payoff actually cannot become negative. And we also assume that there is a risk-free asset. I'll denote it by BT, and it will represent some money market account which has the following dynamics. R is the risk-free rate, T is time, and by definition B at time 0 is 1. Okay, so at the very beginning we have $1 investment in that money market account. Okay, the important thing is that this one is risk-free. Okay, well, since I told you that I'm gonna use the martingale approach, I used so-called risk-neutral valuation formula. I assume that the stock pays no dividends, and we know that from risk-neutral pricing there must be some kind of equality between the ratio of the call price and the expected payoff. Okay, so I basically choose B to be so-called numeraire asset, which will be the relative asset which we use to determine prices. Okay, this is really important. We will use this relative pricing in order to facilitate some computations. Okay, the important is that this one is so-called numeraire. Okay, and from the risk-neutral pricing formula we know that the value of the option at time 0 divided by the riskless account at time 0 must be equal to some expectation, but the expectation is induced by the numeraire asset, so it's some kind of risk neutral expectation of the payoff, the discounted payoff. Okay, don't forget that there is a BT. Okay, but like I said, at time 0 this term is 1, so actually on the left hand side we only have the value of the option at time 0, and this is the value that is of our interest. Okay, we need to get the formula for C0. Okay, well, the problem is in this formula is that there is some kind of dynamics of ST, some real world dynamics, but we have the expectation which is under the risk neutral measure. Okay, so it's risk neutral probability that there is a risk neutral probability that we are going to exercise the option. Usually the dynamics of the stock will be defined in terms of the following stochastic differential equation, which means that the differential of the stock price, the increment, is equal to some deterministic component plus stochastic component. This is volatility. This is again the stock price, and this is the Brownian motion increment. Okay, so this item is random. It actually causes the fluctuation in the stock price. Okay, an important point about this stochastic increment is that it's normally distributed with zero mean and variance dt. Okay, this is really extremely important. Okay, well, this is the real world dynamics. Okay, and like I said before, we have some risk neutral expectation. That means that we cannot use the real world dynamics to determine the value of the stock or the distribution of the stock. We need some kind of difference representation. The risk neutral valuation is based on martingales. Martingale is a process that is without drift. It has drift equal to 0. Okay, and we somehow need to make the relative price of the stock with respect to the dynamics of B zero drift. Okay, so it is important that I define new process Z of ZT, which is equal to ST with respect to BT. Okay, and what we want is that dZT with respect to ZT has zero drift. Okay, this is actually what we want. So let's define what's the dynamics of this process set. By Ito's rule for Ito's quotient rule, we know that the dynamics of such a process is equal to the differential of the stock price with respect to T. Oh, sorry, differential of the stock price with respect to S minus differential of the money market account with respect to B Now let's rewrite this once again, because here comes their product. And finally, at the very end, we have this term squared. Okay, so this is Ito's quotient rule. So let's substitute for ds and s, db and b. One important thing should be pointed out here. dB is equal to, or dB with respect to B is equal to R dt. Okay, so this is the dynamics. This is the differential equation for this expression. Okay, so what we have here is ds with respect to s means ds with respect to s, so we divide and we only have mu dt plus sigma times the Wiener increment minus r dt minus the product of them should have been t minus r dt squared Okay, so now we have to apply some basic rules of stochastic calculus. What we know is that differential of t times differential of t is 0. So is differential of the Wiener process and the differential of time. Okay, so basically this term drops out and so does this one. Okay, and what remains are only these terms. So that equals this. Okay, if we regroup them, we get u mu minus r times dt plus sigma of the times the differential of the Wiener process. Okay, well, and like I said, we are looking for zero drift. Okay, so this really gives us the correct indication that in order that the drift of this process is 0, mu must be equal to r. Okay, this means that mu must be equal to r, or must go to r. Okay, well, we now need to inject, we now need to transform the drift in the S process. Okay, the process of the stock, in order to make it risk neutral. Well, this is done by so-called Girsanov theorem and the change of measure. Okay, let me just go through some basic concepts of Girsanov transformation. Girsanov transformation says that we have some process LT, which is equal to some kind of exponential that is defined as integral 0 to t sum of some function phi times the Wiener process of, there should have been s, minus integral going from 0 to t of the same function squared times ds. This will give us basically new measure. Okay. I know that it sounds kind of weird, but it's just simply so. This function phi is extremely important, and it's so-called Girsanov kernel. Okay, this is the core point of the transformation, and this kernel will allow us to transform the original Wiener process into other Wiener process under the new measure. Okay. Okay, so this is what it basically does. This function. Okay, so sorry. We can substitute this term with this function and the new Wiener process. Okay. And the Wiener process will still be the Wiener process under the new measure. Okay, but how do we get this function? Well, I said that we need to kill the drift of this process. So actually, mu must be equal to r. Well, to do so, we choose this function to be equal to fraction r minus mu divided by sigma. Okay, so we now have this Radon-Nikodem derivative. This is called Radon-Nikodem derivative, and we can transform the measure, and we get new Wiener process under the risk neutral measure. Let me show you. We have this, and now we put this this Wiener differential into the original equation for ds. Okay. So instead of this, use the following representation. Okay, so now ds of t equals this term times r minus u dt times s plus sigma s times the new Wiener process under the risk neutral measure. As you can see, this drift term and that one cancel, and we only have r times s dt. Okay, so let me just use this equation, and instead of that we have r. So this is extremely important. It's the motion of the stock under the risk neutral measure. That is exactly what we need over here, okay, because this is the expectation under the risk neutral measure. Well, this is nice, but we still do not see the solution for s. If you ask me what is s, what's the solution of s, what will be the s at time 10? Well, I cannot answer that, because this is just the equation of dynamics, it's not the solution. Well, in order to solve this equation, we again have to use Ito's lemma. And Ito's lemma says that differential of some function of s and t is equal to differential of f with respect to, or partial of f with respect to s times ds plus partial of f with respect to t dt plus 1/2 f with respect to s squared ds squared. Okay. Well, if I choose a function, say y is equal to natural logarithm of s of t, and I want to check the differential of y, okay, you can define it like that. Okay. And now I'm gonna differentiate according to this rule. I want to check the differential. The dy is equal to, and now logarithm of s with respect to s, well, it's 1 divided by s times ds. There is no t term, we keep t constant, so nothing. From that is nothing. But here you'll get 1/2, and the second derivative of the function, which is logarithm of s with respect to s, well, this is this term and one more derivative of that, so that will basically give us minus 1 divided by s squared. Times, and now what's the square of the differential? Well, we take a look at this equation and we square this equation. I could do that step by step, but believe me or not, the important is only this term, because this one squared is equal to 0, and this term times this term is also 0. So the only term here is relevant, and if we square this, we get sigma squared s squared times dt. Okay, so extremely important property of the stochastic differential is that when it's squared, it's equal to dt. Okay, so here I'm gonna have just sigma squared st squared times dt. Okay, so this is actually equal to, and now take a look, it's ds divided by s. Well, ds divided by s, so what I have here is only r dt plus sigma times the stochastic differential. So r dt plus the stochastic differential without s. Okay, minus 1/2. Well, these two terms cancel, and I only get sigma squared times dt. Okay, if I regroup that, I get r minus this term dt plus sigma times the stochastic differential. okay? But know that that was differential of the function dy, and dy is differential of logarithm s of t. So this is perfectly equal, and if we now integrate between the time 0 and small t, we get logarithm of st minus logarithm of s times 0 is equal to this term times t plus sigma times the linear process at time t. Okay, I can of course move this guy to the right hand side, and I put everything, I actually create an exponential so that I get rid of the logarithm here. So st is equal to exponential of this. Okay, but we know that this is perfectly equal to multiplication of the following logarithms, of the following terms. Yeah, and this one is equal to a 0. So this is actually the solution to the stochastic differential equation. Okay, so this is extremely important, because now I know what the stock price at times t might be. The only random term is this linear process. Okay, fine. Well, how to deal with that? I now take this formula again, and I know that this term is deterministic, and it's equal to r e to r minus r t. Okay, so the only thing I need to tackle is the maximum function of st minus k and 0. So let me rewrite this using slightly different notation. I'll use so-called indicator function. So the maximum of this is perfectly equal to indicator function, or st minus k. You'll get st minus k if the event st is greater, there should be big T, is greater than k at maturity. Okay, this is really the same, believe me, but this is also equal to risk neutral expectation of st times the indicator minus k times the indicator. Okay, well, and moreover I can divide it into two expectations. Usually it is written like that. Okay, there should be expectation, of course, the expectation sign, I mean. Okay, well, honestly, just to tell you, this one is really very simple to solve, because this is just a probability of st is greater than of st being greater than k. So this one is really very easy, but this one is more demanding, and we will need to use one more measure change. So this one is more tricky because here I have the product. Okay, this is just a simple probability of the event st greater than k, but this one is more demanding. Well, let me just denote, let me just focus on this term. If I put this back to the expectation term, I can do that. Then it means that in the denominator there will be bt. Okay, and there is a simple rule that says that expectation times Radon-Nikodem derivative times some event or some variable x is equal to new measure expectation under the new measure, which is defined by the Radon-Nikodem derivative, times the variable. Okay, so somehow I need to get rid of these two terms just by using the change of measure. Okay, so let me try to define the Radon-Nikodem derivative that would do exactly the thing that I just mentioned. Well, if I choose as t divided by pt, what will it give me? Well, I take the dynamics of this divided by bt, which is e to r t. Will it give me the Radon-Nikodem derivative? Well, actually it won't, because notice how this is defined. It's defined like this, which would be fine, but I have some extra term as 0 at the very beginning in my case. Okay, so how to get rid of this term? Well, the term is constant, so it's very easy to work with it. So if I divide it, I define the Radon-Nikodem derivative like that, I get rid of the term. Okay, and this is simple to solve, because we can put the RT term in here. Sorry, I should keep big T over here. Okay, and now you can see that this term and this one, the extra one, cancel. So what I basically have is just exponential of maybe I should use this one as the first one, this one minus this term times t. Okay, and this is really Radon-Nikodem derivative. I can rewrite this as times the integral from 0 to big T of sigma differential of the linear process under the Ritz neutral measure minus 1/2 of the integral going from 0 to big T of squared times Ts. Okay, so take a look at this term and compare it with the definition of Radon-Nikodem derivative. Well, I actually got it. So this kernel, the Girsanov kernel, is equal to sigma. Okay, so I can again exercise the change of measure. I have this Wiener process which is equal to sigma ut plus new Wiener process under the new measure. Okay, and if I take the dynamics, the previous dynamics, and I again substitute, well, this can be also rewritten like without the differentials basically. So this is equal to sigma t plus this term. If I substitute for the Wiener process over here, I get something like that, and this is equal to just plus over here, and that's basically all. Okay, so this is the dynamics of S under the new measure, which is this measure. Okay, well, how do I set up the expectation? Before I had something like this, and I do not see exactly the Radon-Nikodem derivative in it, because the Radon-Nikodem derivative has been defined like this, and I'm not seeing the S0 term. Well, this is very simple. We just rewrite it like, no, we just factor out S0 and put it here again. This can be obviously factored out from the expectation, because this term is known. Okay, so there is no expectation basically. And now we have the Radon-Nikodem derivative inside. So this is equal to S0 times the indicator. Let me take the indicator function times LT. Okay, and like I said before, this is the event x, or the thing x, the random variable x, is equal to just the expectation of x under the new measure. So this is equal to S0 times expectation of the indicator function, where the S has the dynamics defined over here. Okay, so let's go back again to this formula, and C0 is equal to, instead of this expectation and e to minus RT, I use this term, and now I just simply have two expectation terms, and this is also equal to probability under this measure that st is greater than k. And likewise, we have the probability under this measure that st is greater than k. Okay, so let's say I denote this one J1 and this one J2, so this is equal to S, oh no, this is equal to S0 times J1 minus K, I should use this, times J2. Okay, and we are going to tackle J1 first. So J1 is the probability well, what is ST under that measure? Well, ST under that measure will be basically this equation just use the big subscript. Okay, and now I'm gonna go inside. So how can we transform this? Well, firstly I divide by S0, so on the right hand side I got k divided by S0. Okay, now I take the logarithm, so the left hand side is just simply this greater than wait a second, greater than logarithm k above S0. Okay, now I clean the left hand side, I only keep this term there. Oh no, I hate this message. There is nothing worse than that message, so let me open a new window. So I clean the left hand side. Yeah, I know. And that means this guy is equal to what we had before minus that. Okay, and now comes the tricky point. We multiply by -1, so on the left hand side we get minus, but we have to change the equation sign or the inequality, and also change the right hand side. So from the logarithm I'll just swap these two variables. Okay, and here for sure I'm gonna have plus. Okay, but notice that this is in the expectation. One more thing I have to do here. I can divide by sigma. So if I divide by sigma, I get on the left hand side something like this, and on the right hand side okay. And let's go back. I know that it's under the expectation sign, not under expectation but under probability sign. Okay, and now what's the random thing here? What's the random variable? Well, it's this winner process or winner variable. What's the distribution of this term? Well, it's normal with zero mean and variance t. So if we divide this variable with the square root of t, we get standard normal. So this is equal to probability, and we standardize this variable by the square root of t. So we get standard normal over here, okay. So we got standard normal over here. The probability of standard normal over here being less or equal to some number, because everything here is known, so we can define it as, if we name this term on the right hand side, this whole term, if we name it d1, this is the cumulative standard normal of d1. Okay, so if we go back, then what we have here currently, or yeah, it's actually this. Okay, and in the very same fashion we tackle the J2. Okay, this is J2. So J2 is the probability, the risk neutral probability that ST is greater than K but ST has the motion defined by this equation. You can see that it's the Wiener process under that measure. Okay, so it's actually equal to just change the t to big T. It's actually equal to this probability, and again I'm gonna tackle the inside of the squared brackets. So like before, I divide by ST, I divide by S0, sorry, so it's equal to K divided by S0. I take the natural logarithm, so on the left hand side I only have this greater than logarithm of K divided by S0, and I keep only this term on the left hand side, and I moved this one over here, so this will give me this term negative. Okay. Now I can multiply by -1, so that I have this less or equal to, again, switch numerator and why is it like that? Denominator and numerator. And here we got plus. Okay. We divide by sigma. And again, notice that we are actually looking for the probability of this to happen. And we know that this one has distribution normal with zero mean and t variance. So we can standardize this random variable like before. So if we divide by the square root big T, we have 0, 1 standard normal. So we can substitute this one with cumulative distribution function of standard normal. This term is equal to d2, or let's name it d2, this one. Okay, so it's equal to n, the cumulative of standard normal of d2, and it was defined as j2. So if we put everything together, we have the following representation, where d1 is defined by this and d2 is defined by this. Okay, so d1 is defined like that, and d2 is equal to this. Those two equations look very similar. Well, the difference is actually that it's actually d1 minus sigma times square root of time. Okay, and that's all from me. I have nothing more to tell you. I think I've extensively described how to derive Black-Scholes. This is the main result. Okay, thank you for watching my video, and visit my channel again.